So, in this, the 10th lecture, I will talk about constituents of matter, continue with that. So, we will talk about the tau and the new tau, how they were discovered, and then the WZ bosons, which are mediators of the weak interaction, or now we should say, in view of the unification, the electroweak interaction apart from the photon, and finally the Higgs boson, which gives mass to all these particles, of course, except the photon. So, coming to the tau lepton, let's first recall that Kobayashi and Maskawa motivated a search for the third generation of quark, as the three generations were needed to explain CP violation in kaon decays. And of course, the charmed quark was discovered. The tau and the top and bottom quarks were also discovered. So, the top and bottom constitute the third generation of quarks. Independently, Martin Pearl was planning to look, apart from other people, was planning to look for a heavier cousin of the electron and the muon. Both of these are leptons, and it is actually not still clear why the muon exists. I mean, it's heavier than the electron, but it has a quantum number associated with the muon, and so we don't know the reason why. So anyway, Martin Pearl decided to look for a heavier cousin. He led a team that carried out a search at the recently built electron-positron collider at SLAC, the Stanford Linear Accelerator Center. So, the main linear accelerator actually accelerated electrons, and then they produced positrons, then they were cooled in a ring, and then both of these were made to collide in a circular machine called a sphere. And they had a detector there which looked at the products from these E plus E minus collisions through their decays. The experiments of Pearl and his collaboration actually led to the production of a new particle, capital L here indicated by L, and with a mass of 1.622 GeV by c squared. And this given below is the reference for that discovery paper, 1975. So, the detector that they used was the so-called Mark I detector at this facility. So, it consisted basically of charge particle tracking detectors. So, we have the beam pipe at the center, and then the products that come out are tracked in these proportional counters and cylindrical wire chambers and so on. And there are of course trigger counters, 4 of them. So, they are operated in sort of coincidence. And then finally, you have the shower counters for the hadrons, and then beyond the yoke of the magnet, you have these muon wire chambers. So, the iron is about 20 centimeter thick, so that stops the electromagnetic showers and also mostly the hadronic showers, and allows the muons to go through, and these are the ones which get detected in these wire chambers. Of course, the curvature of the track tells you about the muon or any other charged particle that penetrates, that goes through all the momentum by charge. The collision energy was about 4.8 GeV. The theta coverage was between 50 and 130, and of course, in the phi direction, there was full 2 pi detection for coverage. The final state which they were looking for was the electrons and muons with opposite signs. So, they were looking for E plus mu minus pairs or E minus mu plus pairs and some missing energy. The scale of this detector is shown here. So, you can see this is about 1 meter. So, this is of the order of about 5-6 meters in dimension. So, this is the data from the paper that I just cited in the previous slide. So, what is plotted here clockwise from top, go this way, is that there are plots of the electron momentum versus the muon momentum, and they show a scatter, but they are all centered around 1.5 to 1 to 2 GeV, okay, both for the electron as well as for the muon. The next plot is the invariant mass squared of the electron and muon and versus the missing mass. So, you know the missing momentum, you know the missing energy, because you know that you have started with 4.8 GeV. So, you can construct an invariant mass of the missing mass, and you can plot that, and so this shows the scatter plot again, and these are the projections on each of these axes. Finally, the cross section in 10 to the minus 36 centimeters square is plotted versus the total energy. Of course, the total energy should be about 4.8 GeV, and of course, because of the detector resolution and things like that, you get a scatter. But you can see that broadly there is a peak in the sum energy at around 4.8 GeV. Okay. Finally, this plot shows the angular distribution. So, it is peaked around cosine theta compared to the collision direction to be about 0.6 or so, and with a width. So, this enabled Pearl and his collaborators to conclude that they have evidence for a new particle that was produced, and that was called the tau lepton, and indeed for this discovery he got the Nobel Prize. This was in, I think, 1995. He shared the Nobel Prize with Fred Reines, who discovered the electron type of neutrino. Okay, so now we come to the discovery of the tau neutrino, the new tau. This was first detected in 2001 by a collaboration called the Donut collaboration at Fermilab. The new taus were produced through 800 GeV protons from the tevatron dumped on a tungsten target. The principle of detection was that if such a particle was produced, if the new tau was produced, it would interact with nucleons or a nucleus and produce a tau lepton via the charge current interaction and some garbage. I mean, garbage meaning for this experiment. Actually, this would be hadrons, other leptons, or stuff like that. So, of course, this takes place in a target, and we'll come to that. The tau lepton, of course, it turned out has a mean life of about 0.28 picoseconds from the experiments which followed the experiment of Martin Pearl, and so that gave a C times a tau mean of about 90 micrometers. Now, if you want to have a very clear-cut signature of the tau, therefore, it implied that you have to have a detector that should have spatial resolutions of the order of tens of microns. So, from the point where it is produced and x several charged particles come out, that will give you one vertex, and then when the tau decays, that gives you another vertex, and that should be separated by distances of the order of 90 microns, more or less, depending on when it decays. But this delayed event should be a signature of the new tau interacting to produce the tau. Now, the main decay channel for the tau is via a single charged particle 86% of the time, and a new tau. Of course, the new tau being a neutrino, you wouldn't detect it, so you would only detect this single charged particle. So, this is the schematic of the apparatus that was used. So, there is a beam dump in which the 800 GeV protons were falling on this, and they get stopped. Most of the low energy charged particles produced also get stopped in that beam dump, and then there is a dump magnet. So, some of the charged particles are taken away. There is another magnet which again reduces the background. So, ultimately only the neutrinos come through the shield. Then there is another set of veto detectors which says that if there are some high energy muons that come out, they will be vetoed out through these veto detectors. Ultimately, they fall on a detector which we will see in a little more detail in the following slide. So, it actually falls on an emulsion, because these kind of spatial resolutions are possible in an emulsion. Of course, the emulsions are, they don't have too many atoms, so they're not that massive, but in any case, they use these detectors for the kind of spatial resolution that you get. So it consists of a sandwich, a triple sandwich. There is this stainless steel which provides the target material for the neutrino to interact, and then the tau comes out and is seen in this emulsion with very high spatial resolution. These have spatial resolutions of the order of, as you can see, of actually tens of micron, 10 micron of that order. Then, so in between these two layers of emulsion, there is a plastic base, so that basically holds these two emulsions. And then there is another one which has a thicker plastic in between, again, these two emulsions, of course, stainless steel target. And then finally, you have just emulsions. So these are the 4 events after scanning through literally millions of events that they got. They found that there are 4 events in the emulsion. So the neutrino beam is coming from here, it interacts with the iron, this is the dark area. So the target material, the dark area is the stainless steel, in crosshatch is the emulsion, so these thin things here which you see, and then the white is the plastic. Okay, so you can see that there are gaps here, and of course when you reconstruct, you extrapolate the places where you see the ionization, and it turns out, for instance, that here there is a kink, and it is likely that the tau has decayed here to produce this single charged particle. Similarly, here there is a kink, and in this case, you have again some a particle that is produced here, and then there are things that decay and so on. So these 4 events provided the evidence for the tau neutrino. So of the 203 neutrino interactions, there would have been several others which, due to cosmic rays and stuff like that, there are 4 events which are characteristic of tau decay, and the expected background was estimated, of course, from various kind of event rates that they got, to be of the order of 0.34 plus minus 0.05. So you can see that this is more than 10 times the number, and so the probability that these 4 events are from background is of the order of 4 × 10⁻⁴, which is a very small number. 2 of these events, and this is almost background free, these are from tau going to electron, and nu tau and nu e. Of course, these are not observed, you only observe the single high energy electron. Now, of course, you can ask the question that since the nu tau flux is only 5%, because after all the nu tau is created when the tau decays, and in the, let's say, in the stopping material, when the proton stops on this beam dump, and because of the high mass of the tau lepton, you find that only 5% of these are nu tau. Now, is it possible that nu mu nu e flux, which is almost 95% of the total news, could produce this tau-like event? So, from the estimated couplings to the tau lepton, these are quite small. To the nu mu, it's of the order of 2 - 4. To the nu e is about 10 to the -2 at 90% confidence level. A background of only 0.27 plus minus 0.29 is expected. So, these 4 events are much more than the background if such a coupling also exists. So, nu mu nu e leading to a tau-like event. So, the conclusion is pretty strong. It says that the tau neutrino charge current interactions have been observed. Now we come to the discovery of the weak bosons. Weinberg, Salam and Glashow, they unified the electromagnetic and weak interactions, and one of the major ingredients there was the W plus minus and the Z0 boson, with masses ranging from about 80, and so the W plus minus was expected to be about 80 GeV by c squared, and Z0 90 GeV. The weak neutral current measurements in atoms and polarized electron scattering actually confirmed that the, the measurements which were made earlier, they pointed to the unification of the electromagnetic and weak interactions. Now, so these are the three players in this: Weinberg, Salam, and Glashow, and they got the Nobel in 1979. Now, Rubia proposed that we search for these weak bosons at a PP collider. By the way, I should just mention this, I have not included a slide on that. The evidence for the Z0 came about from neutral current mu interactions in a bubble chamber called Gargamel, and that actually preceded the measurements in the atoms and polarized electron scattering. So, these three pieces of evidence together was enough to show that this must be the correct theory for the unification of electromagnetic and weak interactions. Okay, so now comes the so to speak clincher, that if this unification is correct, then there should be these bosons. And Rubia proposed the search for this at a PP bar collider, because in a P you have, let's say, UD and smaller components of S quark and so on, and in the P bar you have the antiparticles, antiquarks, the U bar, D bar and the S bar. So, using these two you can make these weak bosons, and so the proposal was that you use the 26 GeV proton synchrotron at CERN to produce the antiprotons. Now, of course, you produce these antiprotons with a very large momentum spread. So, a cooling scheme was invented by Simon van der Meer, and this meant that you had to reduce the phase space of the antiprotons in 6-dimensional space, in both in real space x, y, z, as well as in momentum space. And this was done using this technique. Turned out to be very successful, and antiprotons were made, accumulated in a ring, and then accelerated in the SPS to energies of the order of 270 GeV or so each. Two detectors, UA1 and UA2, were used to search for these W and Z bosons, and indeed both of them had candidate events, and they agreed that these these events pointed to the existence of the weak bosons, both the W plus W minus as well as the Z0 boson. This happened in about 1983. The UA1 detector here is shown. This is a typical high energy particle physics detector. It has a particle tracker, it has the electromagnetic calorimeter, and then it is surrounded by a hadron calorimeter, and finally beyond the yoke is the muon detector. And so this is the direction of the proton antiproton. So the proton comes in here, and on the back side there is a pipe which brings in the antiprotons. So the UA1 experiment it looked at missing transverse energy spectrum for events where there was one single electron of a very high energy, 15 GeV or so, and there is no coplanar jet. So this is the data that they have, the missing energy versus the events in 4 GeV. So you detect the electron and then you look at the missing energy, and they find that there is a peak here at around 40 GeV or so. And this points to the W boson, and so this is the discovery paper for the W boson from the UA1 collaboration. Similarly, they did the similar thing for the E plus E minus channel and mu plus mu minus channel to look for Z0 events, because the Z0 is neutral, so it can decay into E plus E minus, and then you can look at the invariant mass of these two leptons, and they found that this peaks at around 90 GeV by C squared. Okay, so this is the discovery paper of the UA1 group. Similarly, the UA2 detector also found evidence for both the W as well as the Z bosons, and these are the key papers here, both in 1983. And again, you plot events versus the invariant mass in the case of the Z0, because you can measure the momentum and energy of the charged particles, the E plus E minus pair, as well as the mu plus mu minus pair. And for the W, of course, you have the W decays into a lepton and a neutrino, the corresponding neutrino. So you have a missing momentum. So what is plotted here is the ET distribution for a PT missing transverse momentum by the transverse energy greater than about 0.8, and you can see that this is ET distribution. So this shows up as a as a skyscraper in this phi theta plot. So again, this showed that there was evidence for the WZ bosons from the UA2 detector. Now, as I said already that this involves producing and cooling and then accelerating antiprotons. So, the method that was used by Simon van der Meer was to use stochastic cooling. So, this schema of this is shown here, a schematic where you keep these antiprotons rotating in a magnetic field, and they have rather large dimensions of the quadrupoles that and magnets that keep them rotating, because they have large spatial dimensions as well as large momentum acceptance is needed by those dipoles, magnetic dipoles and quadrupoles. But what is then done is that the center of the beam is sensed by a capacitive sensor, and then the kicker corrects it. It gives a RF voltage that brings it back to the center, and this keeps on happening about 10 to the 6 times a second, so that after a while it settles into a nominal orbit. So, this is depicted here. What is plotted is the revolution frequency versus the density divided by per hertz, and you can see that the injected beam has a rather broad distribution, but after it is pre-cooled in about 2 seconds, 10 to the 6 particles are come together in a with a sort of reasonably small spread in the revolution frequency. Okay. So, the longitudinal cooling, so this is the transverse cooling in the transverse direction, but the longitudinal cooling is done using a pickup and a cavity. So, the slow moving particles on the average, they are accelerated, and fast moving group of particles is decelerated, and so finally you get about 6 × 10⁻⁻⁻ antiprotons, which are then injected into the proton synchrotron to raise their energies up to about 26 GeV, and then they go to the SPS where you can accelerate it beyond 200 GeV. Okay, so this was how the WZ bosons were discovered. An extremely important ingredient of the Weinberg-Salam-Glashow theory was that how do these fields get mass, because otherwise all the leptons have 0 mass and so do the WZ bosons. Higgs and Francois Englert, and of course there are a couple of other people who also worked on this, but by the time this was discovered and these two gentlemen got their Nobel Prize, the other two scientists had passed away. So, they got this Nobel Prize after the confirmation of the Higgs particle, which was detected in two different detectors at the Large Hadron Collider in CERN. So, the Higgs field was proposed, as I said, to give mass to the elementary particles. Even if they were massless to begin with, they acquire mass through their interaction with the Higgs field, which pervades the whole universe, and the stronger this coupling, the larger is the particle mass. The Higgs boson, of course, there is no strong prediction on what its mass should be. It could be anywhere between 50 and 1000 GeV, and there were searches earlier, actually this should be GeV by c squared, but I mean these some of them put lower bounds, some of them put upper bounds, but really this was there is a broad range of energies in which it could have been. So, the LHC, the Large Hadron Collider at CERN, was designed as a 7 TeV on 7 TeV proton-proton collider to search for these Higgs bosons. So, this was a energy large enough, so the center of mass energy would be about 14 TeV, and in principle if you had Higgs boson up to this mass, you would be able to produce it. And this was one of the main goals of the Large Hadron Collider. So, two experiments were set up, the so-called compact muon solenoid and the Atlas, to find these Higgs. They have, although they have different design, but basically both these detectors have an inner silicon tracker Then they have a electromagnetic calorimeter, which measures photons and electrons, showers and so on. Then there is a hadronic part, the hadronic showers are measured, and then the charged particles move or get stopped in the yoke of the solenoidal magnet, which is somewhere here, and then they pass into muon trackers. Okay. So, this structure is very similar, but the details of what individual detectors are used for the electromagnetic calorimeter, for the hadronic calorimeter, for the muon trackers and so on, that is different in these two. To show you the scale of these detectors, this is the size, this is a human being standing by this side. So, you can see it is a huge detector, and this is even bigger actually. I don't know if there is a human being, probably no, I don't know. Yeah, there is a human being standing here. So, you can see that this detector is even bigger than the CMS detector. Okay, so the results from the ATLAS and the CMS indicate a new particle at 125 GeV. Okay, this was both these groups published their papers in 2012, and this is just a small, very small, tiny sample of the data that they presented in their discovery paper uh, given here, Atlas in Physics Letters B 716 and CMS also. So, these are actually back-to-back papers published in Physics Letters. So, observation of a new particle in search of the standard model Higgs boson, similarly observation of a new boson at a mass of 125 GeV. So, both of these groups concluded that the evidence shows that this is consistent with the Higgs boson. They didn't say that we have discovered the Higgs boson, but they said they have discovered a boson and whose properties from the data that they had at that time are consistent with it being the Higgs boson. And the mass of these, as you can see, in this case, it is a plot of the signal to signal plus background for plotted with bind to 1.5 GeV, and this is the invariant mass. In this case, I think it is the gamma gamma. You can see that there is a peak here at about 125 GeV. This is so-called unweighted and this is the weighted. So, these are technicalities, and so this is seen again. This is just a sample of what CMS has seen. They have seen many other channels, and of course, in 2025 they have analyzed literally hundreds of such channels. And similarly, this is for the ATLAS experiment where they plot events per 10 GeV, and you can again see that there is a peak at about 125 GeV. So, in summary, I should say that I have discussed the discovery of the tau lepton, the tau neutrino, and the discovery of the W plus, W minus and Z0 bosons, and finally the discovery of the Higgs boson. Thank you.